Okay, so this is a continuation from the previous video that I did last week sometime where the music was too loud, so I'm continuing it here. I believe I stopped at the slide after this, but we'll go from this slide. So memory, there's just a bajillion different types out there. I'm not going to even pretend to know what they are. I like classifying them in two types. I call them incidental memory and structured memory. So incidental memory is kind of the small stuff we've been working with, like a register or a flip-flop. Flip-flops are one-bit register. Structured memory is what we're going to get into. It's big memory, such as RAMs and ROMs, and relatively large compared to flip-flops and registered. So I think it's structured memory because if you look at it in the underlying layout, it just has this same regular structure over and over again. And in general, memory, hardware-based memory is analogous to arrays in a higher level programming language. In hardware, they're just a set of registers that you can index, we'll say. Well, in an array, you use an index to get into it. Well, this set of registers uses an index also. It's referred to as an address. So to get at each of these registers in memory, we use an address instead of an index. But it's really the same thing as a higher level language array. So there's the basic operation of a memory is that it stores bits, and I like using this little model of a memory here because it's very simple, breaks the inputs and the outputs into three different things. Inputs are and outputs, whatever. There's data coming in and out of this thing. You're reading and writing data. The address points you at a particular piece of data inside that memory, and typically you have some control lines you need to tweak to get at the data, read it or write it. So there's two operations typically we're going to do with memory. We're going to read it or write it. Okay, so when you read it, you're copying something from in the memory to somewhere outside the memory, but you're not changing the memory. When you're writing memory, you're writing data, you're necessarily changing something inside the memory. So reading a memory doesn't change the thing you're reading. When you write an address, it's going to change that data at that given address. So this memory module here, we're always, there's lots of, well, we've heard read and write, but we're also quite interested in the capacity. And capacity of any memory is always, it stores bits, so you can talk about it as storing bits, but typically it's not really an honest way of looking at it. So this memory here, the couple things to notice about it is, number one, the number of things it can store, the number of pieces of data it can store is always a function of the number of address lines. So the number of address lines is, well, the address is an input. The address lines, there's going to be, an integral number of them. And the number of things the memory can store is 2 raised to the power of those address lines, which is m right here. So if you have 10 address lines, you can store 2 to the 10th different things. So the output of this memory, even though it stores bits, these memories are very rarely bit addressable. Typically they send out chunks of data, whether it be bytes or words or who knows what else. But anyway, the width of the output data, have an S there, just to show that you're not going to get a single bit out of this at a given time. So this S here is technically the smallest chunk of data I can get out of this memory at one time. Like I said, they're not bit addressable. You're getting chunks of data at a time, and then if you need a single bit in there, then you have to delve down and get that bit. So the overall capacity in the terms of bits of a memory like this is 2 to the number of address lines times the width of the data output, which we're listing as S here. So if you have something like this and you want to make it byte, how much byte capacity, you're just going to take the bit capacity and divide it by 8. Hopefully we can do an example of that coming up here. Okay, so this is the some examples here of capacities. What we have here is like a 4 by 16, a 2 to the 8 by 32, to 2 to 12 by 24. These are all the bit capacities. If I want to get these into byte capacities, we can try to do this. Essentially, I don't got the tablet working, so we're going to do this. So we just simply take all these things and divide them by 8. So I'm doing this with a mouse. That's why it's so chunky here. Okay, so these are the essentially this dividing it by 8 changes it from a bit capacity to a byte capacity. So many types of memory out there, like I said, but they're all still classified as ROM and RAM. So ROM, read-only memory. RAM is random access memory. So it turns out that both these memories, even though they have different names, they're both random access. So in a normal class, I always ask my class, gee, what does random mean? And it's no one ever knows. And it's really a simple idea. It's the idea that these memories can get at all the pieces of data in the memory in the same amount of time. So this is important because when you have something like a hard drive that's spinning, you have a read-write head that's flying back and forth across it. The access time for those data on that hard drive varies depending on where at any given time the read-write head is. And so it's even worse with a tape drive, but when we work with semiconductor memories, pretty much they're all random access, meaning, once again, we can get at all the data in the same amount of time. So the RAM and ROM, they do have accepted functional differences, and those are RAM, it's random access memory. It's readable and writable, and it's volatile, meaning you turn the power off, you lose the data. Volatile means you turn the power off, you lose the data. ROM, read-only memories, typically you can only read them, but the issue is you turn the power off, you retain the data. So these are the acceptable differences. There's lots of gray areas here, such as your thumb drives, where you can, of course, you can pull it out, you can write to it, you can pull it out, and the data's still there, but you can't write to it. Okay, so this is a new thing I haven't tried before, putting an extra video in here. So anyway, the mic cut out on the last one and right on the last slide, so I thought I would use a different mic and describe this piece of code. This code is actually pretty important. The issue is it's not that complicated of code. So let's step through. This is a Verilog model of a generic RAM. Now the issue here is the inputs are essentially three control inputs and a data input, and the output is the data. So first thing to notice is it's a parameterized model, which means it's generic, and it will use these parameters unless you override them when you instantiate this thing. So the thing of interest here is the width of the data. The width of the data is this M value, which is used as essentially an array. So once again, it's used as an array. So it's 0 base, 0 to M minus 1. M is 8, so it's 0 to 7, which is 8 bits long. Okay, so that means the data coming on the input is 8 bits long, and of course the data going out is 8 bits long also. Now this thing is this RAM is pretty much modeled like an array. They're very much like arrays anyway. So it's essentially two dimensions. One dimension is the data width. The other dimension is the number of elements. So the number of elements is related to the number of address lines, which you can see here is this n value. N is 6, 6 minus 1, 0 to 5. That's 6 items. So this is actually a 64 by 8 RAM. So there's 64, it stores 64 8-bit values. And so what's interesting here is the way it accesses the read and write. So this is actually the read code here. And as you can see, it's asynchronous because there's no, the output does not depend on a clock. And so the notion here is this is sort of the array here. The array element, it's reading the index, which is the address. The address is how I'm going to get at each value in this RAM. Is not really an index, but it's essentially it's just the value on the address lines. But it's going to go into memory, grab something, and stick it on the output lines. It does it automatically. I don't have to send it any other control lines other than the address. So the output, I'm sorry, the writes are synchronous because check it out, it's based on a positive clock edge as well as another piece of control here, which is the write enable. So to be able to write data to this thing, which means put new data into it, it needs to have a clock edge, and I need to assert that write enable signal. Once that happens, the input data here gets fed into this memory model thingamajobber here, and that's essentially it. It's very simple object. It's easy to use. When you use this in your experiment, don't change these parameters, just change the parameters when you instantiate it. And so lastly here is I have just a model of the RISC-V architecture. Nothing to say about that. Let's call it done.